Remember that novel, maybe you read it in high school or college, A Tale of Two Cities? Well, I'm going to give you a tale of two prodigies. As you know, if you remember back to the very beginning of this Nugget series, we were talking about our hypothetical, our scenario of you going to get a job at Nugget Lab. And you are my prodigy, my friend, the one I'm trying to help in a very quick period of time get ramped up to go take over this job position. You know, that week-long or even weekend-long crash course for Junos and Juniper. Well, let's imagine if I had another prodigy, another person that's not like you, somebody who, let's say, kind of hung with me for a few nuggets. Maybe they got up to the, oh, I don't know, router interfaces part or the routing essentials where we started looking at static routing. And they just said, you know what, Mike? Let's just skip all this stuff and go right to configuring our router. I want to configure my router. I want to configure my switch. Show me how to configure dynamic routing. Show me the commands for routing policy, for firewall filters. How do I do class of service? How do I do monitoring? How do I do maintenance? Just go ahead and let's just skip all of this foundational stuff and let's go right to it. And let's say with that particular prodigy, not yourself, I went ahead and granted that wish. And I went right from static routing. We just started jumping onto the equipment and started going through some configuration. Well, what happens 2 weeks later when that other prodigy gets on the job? Well, in about, I don't know, maybe 48 to 72 hours, I'm going to get a phone call. And they're going to go, hey, look, here's the deal. Remember all that stuff you showed me, all that stuff we went through on your equipment? Well, the problem is the equipment and the configuration and the topology here at Nugget Lab, it's not the same as the example we went through. And I can replicate the configuration and the stuff that you showed me, but I don't really know what to do with all of this equipment here and this topology. And besides, they want me to go to another branch office which has different equipment and a different topology and start working on their stuff. And you know, you never really showed me, Mike, how to work on all that different equipment and those different scenarios. And that's when I'm going to say, but here's the problem. If you would have stuck with me and you would have been there and you would have gone through that essential information on dynamic routing protocols, on vector protocols, on link state protocols, if you would have stuck with me on the routing policy nugget, which we're doing right now, and beyond, you would have been ready for those different scenarios. Why would I say that? Well, because networks are like snowflakes. No two networks are the same. And you must have under your belt a fundamental understanding of how things work and why they work a certain way before you can actually go and start doing it in the real world. In Routing Policy Part 1, we're going to look at 5 main topics, building a foundation for routing policy. We're going to look at protocol independent properties, specifically static routes, aggregate routes, and generated routes. We'll also get an overview of routing policy, what we do with it, why we use it. We'll look at some default routing policies, all of these particular protocols, BGP, ISIS, RIP version 2, OSPF, they all have a default import and export routing policy. And then we'll look at the construction of a routing policy, the elements, the terms, the from statement, the then statement, and then we'll look at some common match criteria. This will all set us up for Routing Policy Part 2. Okay, to begin our discussion on routing policy, we're going to really take it where we left off in nugget number 8, okay, where we looked at static routing. We created static routes between this J2320 and the 2350. And the static route, as we know, had a next hop of the loopback address. So the next hop type for that particular static route was an IP address, which was the loopback of 192.168.2.1. Now, the next hop type could also have been the interface address right here on GIGI 002 at 172.20.66.2, okay? And as a matter of fact, there's other next hop types as well. And that's important. Why? Well, these independent properties are extremely valuable tools to know about because it plays into our routing policy. Now, a routing policy, and if you have to write this down, go ahead. But in a nutshell, a routing policy is basically a way to solve some specific network problem or address a network requirement. Or put it this way, we're going to control what routes get installed into the routing table, so it can be chosen or selected as an active route. We also want to control what routes are exported from the routing table. They can go to some other protocol, or they can go into the forwarding table. Or we might want to modify the attribute or the characteristics of a route, either when we receive the information, or, remember OSPF, when we advertise that information to other peers. Those are all valid reasons for having a routing policy. Controlling the reception, controlling the transmission of routing information or metadata to make changes to route attributes. And since we have defaults, okay, there's default policies for all of these routing protocols, what we're really saying is we want to take some action to override or modify the default behavior. And I'll show you those default behaviors here in a second. Now, so we've talked about the static route, and we know that the next hop type could be an IP address. It could also be an interface. But the next hop type could also be to discard the packet. Okay? Remember, discard is basically saying I want to silently drop the packet and not, I repeat, not send an ICMP error message. And that's a good thing because it countermeasures denial of service attacks and flooding attacks and spoofing attacks. We can also say the next hop type could be to reject, REJ. Now, reject is going to drop the packet or send it to the bit bucket, but it's going to generate an ICMP error message, the destination unreachable message. And so often what we do is we'll use these types of next hops to kind of what we call nail up the route, nail up the static route so we can send certain traffic that might be a security attack to be discarded or rejected. Usually, however, the next hop of a static route is an IP address, like we did in our previous example. And before a static route can be active, it has to have a valid next hop. Okay? Now, the other type of route type that we're going to talk about is the aggregate route. If you come from a Cisco background, these are what used to be called summary routes. Okay, let's fantasize for a second that these two routers here are not the enterprise edge routers of Nugget Lab. Let's say instead that you are working for a service provider, and these routers here are connected to other routers and other autonomous systems on the backbone of the internet, right? Does that make sense? Service providers or telcos connecting to each other, other points of presence. Now, as we know, there are many devices on the internet, and those devices have IP addresses assigned to them, right? Well, here's the deal. If I want to advertise routes from this ISP router to some other ISP router here, do I want to advertise all of the routes that this particular router knows about? Think about it. If I did that, if I advertised to this other router here all of the routes that I know about, and every other router on the internet did that same thing, service providers saying, hey, I know about all of these routes. Can you imagine how large the routing table of the internet would be? And by the way, it's already really large. So what we do is, instead of sending a list of all the routes that we know about, what we do is we kind of aggregate or summarize at some higher supernet or some higher bit demarcation. Okay, so for example, if this router knows about, we'll say, the 172.100 through 120 network, what we could do is we could simply aggregate and say, I know about the 172.20.0.0/16. And I can basically let this router up here know that anything that's in the 172.20/16, I'm the router that you need to send those packets to. Because I have 100.0/24 and other networks that are part of this larger supernet. Okay, so instead of having to send all these routes and advertise them up here, I just simply have this one aggregate. I aggregate them, I summarize them all together. And usually what you're doing is you're kind of moving this CIDR prefix back to the left. so you can represent more networks. And so this aggregate route is a special kind of route that you have to generate and create on these routers so that other routers know how to get to these router prefixes. So let's say this router connects to another service provider, right? I'll put I here. Let's say I configure an aggregate route on here of 10.1.0.0/16. Now, for this route to become active, it has to have a contributing route. Now, a contributing route, let me write this down, is really going to be a more specific or a route with a longer prefix that's part of the 10.1/16 address space. So, for example, if I had a route on this router that I either configured statically or I learned about that is 10.1.1.0/24, well, are the first 16 bits the same? Yes, 10.1 is the same as 10.1. So this would be a contributing route. This contributing route would then make this aggregate route active. And I have to have at least one contributing route to make this aggregate route active. So I could let other routers and other networks know that, hey, if you have a packet destined to 10.1/16, I'm your man, okay, or I'm your woman. And then I would also know about these other more specific contributing routes, and I could send the packets on other interfaces to these more specific routes. So it's the longer mask, the more specific mask, that makes it a candidate to be a contributing route. Now, if I had another route on this routing table that was, let's say, 10.20.1.0/24, well, that's not going to be a route that's going to activate this aggregate route, because this is 10.1/16, and you can see here this is 10.20. So the first 16 bits are not the same. So it's not going to make this route active, this aggregate route active. And this is very common in things like BGP. And this is where routing policy comes in, right? Because with routing policy, and I explain what it is, we can actually control the set of routes that are allowed to contribute, to be candidates to contribute to an aggregate route. So we can control when this aggregate route becomes active and when it's going to be advertised to, let's say, a BGP peer or another point of presence on the internet. Remember, only active routes, listen carefully, only active routes are going to be subject to our routing policies. So we can use routing policies to influence when certain aggregates like 10.1/16 are going to be advertised by a routing protocol like OSPF or BGP. And by the way, this route right here, 10.1.1.0/24, it can only contribute to a single aggregate, which is this one right here. Now, here's a question. Could this aggregate route of 10.1.0.0 actually participate and be a contributing route to, let's say, over here, 10.0.0.0/8? Absolutely. Right? Because this is /8. Do the first 8 bits match? Yes, 10 and 10. So this aggregate route here could actually contribute to another higher level aggregate. Now, what's interesting is, look down here. There's only 2 different next hop types, reject or discard, which is interesting. Why would I make an aggregate route active by having a contributing route go to it and then have the next hop type be to reject or discard? Okay, let me clean this up. Okay, now why are aggregate routes? How come they only have a next hop of reject, which is the default, or discard? Why? Here's the reason. Aggregate routes, listen carefully, are never used for forwarding. Okay, now they can kind of gather up plenty of traffic and let other people know I know about more specific routes, but the next hop is always discard or reject. You never forward traffic to an aggregate route. What you're forwarding to is to a more specific contributing route that activated that route. Okay, so in other words, this router has an aggregate of 172.20/16. it gets a packet from a neighboring router that it knows about this particular 172.20 network because it advertised it to it. But what it's really going to do is it's going to forward the traffic to the contributing route at 172.20. Whatever, okay, 1.0/24 network. So the contributing routes are the ones that we're forwarding to, not the actual aggregate itself. So the aggregate itself has a next hop of reject, which is usually the default. Okay, so we'll just stick with that. So to repeat, the aggregate or the summary is letting everybody know, hey, I know about this particular 172.20 network, but then the next hop will be to reject that, and I'm going to be basically forwarding to one of the contributing routes. And I can have quite a few contributing routes here. The contributing routes are basically longer prefixes, okay, at least /17, right? Longer prefixes within this 172.20 address space. So those will be where we forward them to. Anything with a longer CIDR prefix. Hope that makes sense, because this is used a lot, especially on edge devices between domains and between areas and between autonomous systems. We don't want to advertise to our neighbors all the routes that we know about. We want to advertise to them that we know an aggregate of a bunch of routes, a summary of a bunch of routes that have longer prefixes. This keeps our routing tables relatively small, even when we have just a handful of devices. And again, aggregate routes have to be first configured and then advertised. Now, aggregate routes and generated routes have two important things in common. Okay, number one, they both have a routing preference of 130. Remember the routing preference table we saw earlier on? So it's a pretty high route preference. A static route is going to take precedence over a generated route. So they both have a preference of 130. And the other commonality is they are both activated by a contributing route. Really, the best way to describe a generated route, to make this as easy as possible, is think of this as the route or the gateway of last resort. So it's going to install the next hop that's associated with a preferred contributing route. So it can be used, and it is used, to forward matching traffic. So typically, it's matching a more specific route and is therefore routed when a more specific or longest match is found. And as I said, usually forwarded to the gateway of last resort. So a generated route can actually have two types of next hops. It can be discard, which means it's going to send an ICMP error message, or it's going to be sent to the preferred contributor, which is the default behavior, and the preferred contributor is usually the gateway of last resort. You're not using static routing, and this is the most specific contributing route that you have for a particular packet that's being forwarded. Now, again, this all plays into policy, and this will make much more sense as we actually get into our lab environments. But as you can see, we need some mechanism, we need some rule sets in place to help deal with some of these protocol independent properties, because this is independent of RIP version 2 or OSPF or ISIS or BGP. That's why we call them protocol independent properties. That's why you have to kind of understand these route types, statics and aggregates and gateways of last resorts, before you even get to the specific dynamic routing protocol. Does that make sense? Okay, as far as routing policy goes, let me reiterate what I said earlier, okay, and on my definition, my overview. The goal of a routing policy is to control the information flow, to control the data flow to the routing table and from the routing table, okay? You can apply a routing policy as it comes into the routing table or ingress, or as it leaves the routing table or egress. We can use the routing policy to determine which routes we want to accept or which routes you want to reject, accepting routes from neighbors or rejecting routes from neighbors. Again, BGP peers, OSPF peers, RIP version 2 peers. It also allows us to decide which routes we want to send to our neighbors, and to some extent we can actually dictate some of the routing attributes. And I say to some extent because it depends on the routing protocol, okay? Some allow more than others. Now there's two main types of policies. There's import policies, ingress, and export policies, egress. And all of our protocols, they all have a default route policy. And of course, we could just use the default route policy, or if for any of these reasons we have to make changes, we would create our own route policies. Let's look at a diagram to help explain what's going on here. Okay, take a look at this crudely constructed diagram here. What's the goal of routing policy? Well, it's to control the way information flows into the routing table and out of the routing table. So obviously, if we're controlling information going into the routing table, that would be our import policy, right? And if we're controlling traffic coming out of the routing table, that would be an export policy. Now, by the way, our export policy can be here, but as we mentioned, our export policy can also export to the forwarding table. So here's our packet forwarding engine here, PFE. So we really import information either from other protocols, information that's received from dynamic routing protocols like OSPF or BGP. It could also be information we get from other neighbors. Whether it comes from protocols or from neighbors, the import policy is basically going to apply itself before we place the routes into the routing table. So we could actually modify the routes that are available in the routing table, which would affect the local route selection process. It'll also affect what would get ultimately exported into the forwarding table, or what would ultimately be able to be exported to other protocols or to other neighbors. Now, policies that are going to dictate how our Junos sends routes from the routing table are called export policies. And we're exporting information to other dynamic routing protocols, or to other neighbors, or to the forwarding table. Now remember, only active routes are available for export. Very important. That's why I started out this whole thing looking at static routes and aggregates and generated routes, because remember, and I showed you how those become active, right? What the contributors that make those active. Because only the active routes are subject to be exported. And only the active routes can have attributes modified, okay? You can't export inactive routes. For example, let's say you have an OSPF route to 10.1.1.0/24, that prefix. But you also have a BGP route to that same prefix, 10.1.1.0/24. Well, remember, OSPF has a router preference of 10. BGP has a route preference of 170. We talked about that earlier in this Nugget series. Well, the OSPF route is going to be the active route, right? Because it has the lower preference. So the export policy could figure out if it wants to send the active OSPF route and if it wants to maybe modify some of the attributes of that route before it sends it to the forwarding table or to another protocol, to another neighbor. However, the export policy cannot send the inactive BGP route. Okay, very important distinction. Now, I mentioned earlier that, all of these protocols, BGP, OSPF, ISIS, and RIP, they all have a default routing policy, a default import policy, and a default export policy. And these are in place. They're activated. They're part of the Junos operating system. So let's look at a table that describes those, and of course we have to memorize those, because remember, our own user-defined routing policies are basically creating differences. We're overriding the defaults. Okay, we can see in this table that I created here, it's not completely perfectly proportioned, did it by hand, but you can see we've got 4 protocols here: OSPF, ISIS, RIP, and BGP. Every protocol has a default import policy, got a column for that, and a default export policy. And you have to basically memorize this. There's just no two ways about it. Now, the default OSPF import policy is basically to import all OSPF routes. So we're going to accept all OSPF routes and import them to the inet.0 routing table. Remember, as a link state protocol, OSPF is going to store that link state database throughout each OSPF area. And it does this by flooding LSAs, link state advertisements. Now remember, this is important. You can't apply a policy to affect the way the local link state database is maintained or the way the LSAs are flooded. They don't send and receive routes directly. Remember, they go ahead and flood these in the LSA packets. Those are what are used to build the topological database, which the router uses to compute the routing table. So basically, link state protocols like OSPF and ISIS don't really support a whole lot in the way of an import policy. If you want to filter LSAs, we want to use protocol-specific mechanisms that are specific to OSPF and ISIS. Notice the export policy is to reject everything for ISIS and for OSPF. Why? Because the default behavior is to do LSA flooding. Also, you can't apply policy that is going to prevent the software from installing internal routes in the routing table. Okay? Because remember, a link state protocol works under the assumption that all of the devices, all of the neighbors, have the same routing information for internal routes. That's how we make our consistent forwarding decisions. If you were able to block an internal route from entering a routing table on an OSPF or an ISIS router, you could cause certain prefixes to become unreachable. You could create routing loops. Now, the default export policy for OSPF, like I said, is to let the system always flood LSAs through the OSPF area. So what the default export policy will do for OSPF and ISIS is basically block the advertising of any additional routes from any other sources to the OSPF or ISIS neighbor. Now what about RIP? Okay, RIP has an import policy that is to accept all routes learned from the explicitly configured neighbors and to import that to the inet.0 routing table. So the software will ignore routes learned from neighbors that aren't explicitly defined within your RIP configuration. So if you want to advertise any routes to your RIP neighbors, you have to configure an export policy that matches and accepts RIP routes. So the export policy here is to reject everything. You have to explicitly configure a policy that overrides that and matches and accepts RIP routes. What about BGP? Well, BGP is going to accept all BGP routes and it's going to import that into the inet.0 routing table. Okay? Now, what is the export policy? Well, this is where things get different. BGP's default export policy is to advertise all the active BGP routes. And so this is really the most robust and most flexible, because with BGP we can configure import policies and export policies at the BGP protocol level. We can do it based on a group of routers. We can even do it on a neighbor by neighbor basis. So these are our default policies. Make sure you memorize this information. Okay, I'm over on the 2320, and boy, it's been a while since we've been in the Junos, hasn't it? Seems like a while, but I'm over here in operational mode, and remember, I want to reiterate this fact that link state protocols like ISIS and OSPF do not send routes directly. They don't receive routes directly. Remember, they flood LSA packets. That's what's used to build the topological database that the routers use to compute the route table. So, like I said, as far as import policy goes, OSPF, ISIS, pretty thin, okay, pretty thin. But I want to show you something about vector protocols, okay? So, vector protocols like RIP, the distance vector, and BGP, our path vector protocol, they actually have the ability to support something known as received routes and transmitted routes. So here in operational mode, if I do the show route command, and we can see that we can do received protocol or receive protocol followed by the question mark. You can see I can support this command for BGP or RIP, and I could follow up BGP, for example, or RIP with the actual IP address of the neighbor. Okay, so I can show the received routes from a neighbor. I can also show the advertised routes of a neighbor, BGP and RIP. So we really have more robust application of import policies especially and export policies with BGP and RIP because of this directly receiving and directly transmitting of routes to neighbors. And that's why I mentioned back in that table that, like, for example, RIP, it's going to accept all the RIP routes from the explicitly configured neighbors, and that BGP would accept all the BGP routes from its neighbors. And BGP, for its export policy, will also accept all active BGP routes. Where BGP and RIP differ is that RIP pretty much rejects everything. Now, of course, these concepts I'm showing you here, we're going to solidify these concepts as we move forward in the JNCIS especially. But again, we're building a foundation here. Now, something else I want to mention here is the fact that, generally speaking, policies can be applied at 3 levels. They can be applied at the protocol level, so proto. They can be applied at the group level, okay, so a group of devices. They can also be applied at the neighbor level. I'm just going to put NEI, okay, as to which level they can apply their policies, okay. Now, obviously, this is going to make more sense as we move along, but it's important to just have this reference, okay. So, let's start at BGP at the bottom, okay. BGP is the most robust. You can configure import and export policies. So I'll put I and E. These can be applied at the protocol level, they can be applied at the group level, and they can be applied just from one neighbor to another. Now, OSPF and ISIS, and we'll just forget about ISIS for now because really we're not going to deal with this until JNCIS. But let's just look at OSPF, okay? As I mentioned, since link state protocols are going to be depending upon the participating devices in the area to have a consistent link state database, we configure our import policies and our export policies only at the protocol level. Okay, so proto level only for OSPF. For RIP, you can configure import policies at the protocol level and the neighbor level. You can apply export policies only at the group level. So you can only have an export policy going to a group of RIP routers, okay? And again, this is really more of a reference right now, but it is information that we'll need to know and understand as we move forward in our knowledge. Okay, let's look at the components of a routing policy. Here's my user-defined policy here. It's called Nugget policy. Now, a routing policy is made up of a ordered group of terms, okay? So you can see here these green boxes represent my terms. So we'll say this is a term, and the name of this term is first, okay? The next ordered term we'll say is called second, and then here's a term which is called third. Very logical. So these terms are important because they're kind of the fundamentals, the building blocks of our policy. And a routing policy typically has at least one term, but technically it can be 0 or more terms. And it's a whole lot like if you're any kind of programmer, if you know if-then statements, for example, if all of the match conditions that are specified are true, then something else is going to happen, or then this will be executed, right? That's what we're kind of talking about here. So we've got this first term, and we have the first component, make a box for it, is from. So from is really kind of the if part of it. From statements are really there to describe things that we're going to match on. Okay, and so what we're going to do is we're going to sequentially evaluate these terms until you either get to a terminating action or the end of the policy. So if we reach a terminating action in the first term, we won't even go on to the second term or the third term. Okay, so whatever the from is, if there's a match, we then go to the then part. So if we match the condition in the from, we then execute the then component or the then statement. The then is the action that we take if there's a match in the from statement. Okay? If not, we go to the next term, where here we have a from. If there's a match of that from statement, then we're going to take this action. If there's no match and there's another term, we then go to the third term, where here we have a from to evaluate. If there's a match, then we'll execute this action. Now, at this point, if there is no match, well, that's the end of the policy, right? So there'll basically be no action. Now, if a terminating action occurs within any of these terms, these named objects called terms, then at that point, we'll take the terminating action, and that'll be the end of that policy. Now, when you're evaluating your from statement, okay, or the criteria that we're going to match on, the Junos evaluates as a logical OR between arguments to a single match criterion, and a logical AND between different match criteria. Let me put it this way. If you want this from statement to be considered to be true, the item that's being evaluated has to match at least one of the arguments to each given match criterion. Now, we're just looking at logic right now. When we look at some real examples, of course, and our little case study, this will make this a lot clearer. Now, if a route, that's what we're talking about here, right? If a route matches all the conditions in the from statement of a term, let's say term first, Junos will execute all of the actions specified here in the then statement of the term. Now, if one of these actions is a terminating action, right, then the policy stops. Now, what are the terminating actions? Well, accept the route or reject. Those are terminating actions. So the software will take the accept action or the reject action, do it immediately, and there's going to be no further evaluation of our policy. So we'll never get to term second or term third. And again, first, second, or third, these are just names. These are just logical, user-defined names for these components. Okay, so we have this logic down. Let's focus here on the from aspect, because we want to really look at the common match criteria for our routing policies. Let's explore some of the commonly used methods to match in the from statement, okay? In other words, when we're selecting routes, in the from statement, we can select those routes based on the protocol, whether those routes are static routes, whether they're from the OSPF protocol or BGP protocol. Let's skip down here. We can also match the criteria of the route based on, let's say, BGP's AS path. Remember, BGP is a path vector protocol, and so it doesn't have a hop. It has a list of autonomous systems that it moves through. That's its hops. So we can actually look at the attributes of the AS path to match on. We could also match on something like the OSPF area ID if we wanted to. We could also say let's match on whatever the next hop is. What's the next hop interface? What's the next hop IP address? Or is the next hop discard or reject, right? So we could match on that. The two most common methods that we use to match on routes is obviously based on the prefix. So, for example, 10.10.10.0/24, okay, that particular prefix, we can match on something like that based on a route filter or a prefix list. So those are two very common ways. And again, what are we trying to do here? We're trying to select a route based on some criteria, and that's our from statement, because we're going to take some action with the then statement, right? If we find a match, then we're going to take some action. Now, what if the policy or even the individual term doesn't have a from statement? Okay, that's a possibility. If you don't have a from statement, if you leave it out from, let's say, term first, then Junos is going to subject all of your routes to whatever action is in the then statement. Okay, so there is no differentiation, right? There's no way to weed it out by matching some type of criteria. It's going to apply to all the routes. Now, this is just a subset of all of the available match criteria, but this is a pretty good list for us here at the JNCIA level, so we're going to kind of stop here. All right, well, in routing policy part 1, we looked at protocol independent properties. We also got a nice overview of routing policy, the what, the when, the how, the why. Looked at some default routing policies for BGP, RIP version 2, OSPF, and ISIS. Looked at construction of routing policies, the components, and then finally some common match criteria. I hope this CBT Nugget has been informative for you. I want to thank you for viewing. We'll see you in Routing Policies Part 2.